Thank you. Thank all of you for staying here until this late hour Friday afternoon. And thank you, Enrique and Gesa, for organizing this nice workshop, giving me the opportunity to present some recent research on quantum systems in ladders. This is a ladder. And exotic phases that we can observe in these geometries. So ladders are actually getting popular or have become popular in different platforms. So there were exciting experiments with cold atoms and optical lattices, which have this ladder structure. So since 2014 in Emmanuel Bloch's lab, there are of course also Rydberg arrays which can be brought in optical tweezers into this ladder geometry. Then there are also experiments with electrons where ladders play a role. So in Delft they have quantum dots which are arranged in ladder geometries, essentially because the systems are small, and so ladders are like the easiest way to get something which is a little bit beyond 1D. There are also then optical photonic lattices with ladder structures. And let me finally also mention, last but not least, molecules, polymers like graphene nanoribbons, which which have a elongated structure in one dimension and very compact in the other. So in a sense are also ladder-like systems. So these are examples for different ladders that we can find, and so it shows that ladders are really experimentally relevant and experimental friendly setups. And the nice thing is that actually ladders are also theory friendly, and this is now a picture that we have seen already this morning, and that is about a variational technique that is very efficient in 1D and 1D and quasi-1D systems. And this is the MPS method that is illustrated here in this figure. So what we have on the left side is a general wave function which depends here on certain external degrees of freedom. So these are these legs. And the idea of this variational technique is to decompose this object into simpler objects, tensors, where each tensor is only connected to one external degree of freedom. And then, of course, I mean, this is an object which entangles all these external degrees of freedom. So what we have to make sure then is in this ansatz that this entanglement which is present in the wave function is also present here. So, and that means it has to go through these legs. And that means this internal dimension of these tensors has to chosen large enough so that this structure can actually accommodate the entanglement in the system. And if this is the case, then we have a good ansatz. And now in 1D systems, there is something which makes this ansatz very efficient. I mean, in typical physical states, also beyond 1D, there is an entanglement law, which is called the area law. So this is what means that the entanglement of a subsystem scales with the area of the subsystem. And in 1D, this means actually that the entanglement between two subsystems is, I mean, it's just a constant. Yeah? It does not scale with the system size. So we have this entanglement very bounded, and that makes this so efficient because it really means that the entanglement which has to flow through some internal leg is limited, and that allows us to use this ansatz very efficiently. Yeah, and that works in 1D and in 1D-like systems. So it's an ansatz that can be used to treat ladder systems. So ladders are theory-friendly objects. Now, you may think, okay, I'm just looking for some simple geometry, then why not directly go to 1D chains? So this is even simpler than a ladder. But of course, the reason why we're interested in ladders is that it's like the simplest geometry which allows to go a little bit beyond 1D. So and to explore some phenomena which really are not possible in 1D, but and one example that we will see today is D-wave pairing. So these are pairing correlations in quantum systems which have a non-trivial structure in at least in along two dimensions. So a pairing wave function like this, for instance. So this is the dxy pairing, or this dx square minus y square pairing looks just rotated. And these pairing channels, actually, they are very important in nature. So this dx square minus y square pairing is the pairing mechanism which in cuprates is responsible for the high temperature superconductivity in these materials. Now, how do we get such pairing correlations in ladder systems? So we need, of course, some interactions which produce such correlations, and it is known since this early work in Matthew Fisher's group in Santa Barbara. It is known that actually there is one type of interaction, namely ring exchange interaction, which really enforces such D-wave correlations in Bose and Fermi-Hubbard systems. And yeah, so this is how ring exchange interactions look. So they are non-local interactions on the plaquette of a ladder. So you have two particles here sitting on the diagonal of a plaquette, and then the ring exchange just rotates them. So it's like a correlated hopping process where these two particles move along the plaquette. That's the interaction which would really be very nice to have if you want to have D-wave correlations. And my talk now today will, in the first place, discuss how we can actually get such interactions in a synthetic quantum system, and I will show you how we can get such exotic ring exchange interactions in a system of trapped ions, how we use these systems to actually first build a synthetic ladder, synthetic dimension ladder, and then we will have the chance to have tunable ring exchange interactions there, and we will see that this gives rise into a D-wave correlated Bose metal phase. And then in the very end, I will very briefly also switch to a fermionic ladder and show you how this D-wave paired phase actually can modify there by band flattening terms. Yeah. So this is a chain of trapped ions. So if you take trapped ions and throw them into a Paul trap, then what these ions do is they align. So you have a 1D structure, and one typical thing that is done with these trapped ions is that you prepare them in two possible internal states, and then you have something like this. You have a spin chain, yeah? And you can spin 1/2 chain, and you can, of course, map spin 1/2 objects onto a hardcore boson. So you just say this is, let's say, an occupied side, and the spin down is an empty side. So then you have here a chain of hardcore bosons. Now we would like to have them move around, so we produce some hopping of them. And hopping then means actually some spin flip interaction, and spin flip interactions can be engineered. This is one way how to do it. So you add Raman couplings to the spin to the ion chain, Raman couplings which flip a spin and create a phonon. This is the blue coupling, or you may also have a red coupling which flips a spin and annihilates a phonon, and you make these two couplings off-resonant, but in such a way that actually only the combination of two beams, for instance a blue and a red beam, then hits the resonance and flips two spins. So that is the scheme that can be used to engineer spin-spin interactions in different in different types of interactions. I mean, here this is for an Ising type of interaction. You can also engineer XY interactions, and yeah, so they are phonon mediated, and so this original idea actually comes from this paper from 2004 by two Spanish physicists, Diego Porras and Ignacio Cirac, and this since then has been realized in many labs in the world. And now what we thought so propose in this recent work, I mean, this is Saurav Biswas, who is now in Alberta, and Enrique Rico, who is here, and myself, is to take these ion chains and actually not let them be only spin 1/2 chains, but have a third state, so 3-level ions, and then then this looks. Oh, sorry. this looks like this, so it looks like a spin 1 chain. But then if you make this bosonic mapping again, this doesn't map onto a chain, but onto a ladder, actually. So you can say this state corresponds to a boson in the upper leg, and that state here on a boson in the lower leg, and the 0 state would correspond to an empty rung. So you have, like, again, hardcore bosons. I mean, the hardcore constraint extends in this case on the rung, so there are no more than one boson per rung. But yeah, so then we have actually here like a synthetic ladder structure through this mapping of 3 level ions onto ladders. And then the hopping again is a spin flip between up and 0 for the hopping in the upper leg, and 0 and down for the hopping in the lower leg. But then a spin flip between down and up, this is actually exactly this ring exchange interaction which we want. So with that system, we can really easily then get hopping and ring exchange interactions just through Raman couplings, and then with that we have what we want. And now if you tune the ring exchange interactions, so you make them stronger, you see in the spectrum of the system there is a phase transition from actually a ferromagnetic regime into a regime where then the system becomes unpolarized. And then if you look on the momentum distribution of the bosons, I mean, we map the spins onto the bosons, and you look at the momentum distribution, you see this kind of function, which has this plateau, which looks very much like a Fermi sea, but it's boson, so it's what I call a Bose sea. And I mean, this analogy really, I mean, I think is appropriate, because if the extension of this sea is controlled by the filling of the system, so you control the number of bosons in the system by the number of ions which are in state up or down, and you can change that, and then accordingly the extension of this sea changes. Apart from this curious Bose sea behavior, then also these bosons are correlated through pairing correlations. In particular, these are correlations of pairs that are on the diagonal of the ladder. They are correlated with pairs on another, either parallel or perpendicular diagonal. They spatially look like this, so they look opposite for the parallel and anti-parallel pairs. So it's really this DXY structure that emerges, and most importantly, in this large ring exchange regime, the decay of this correlation goes algebraically. So we really have quasi long-range order in that system. So it's a D-wave correlated Bose metal phase. All right, now I think I have a little bit of time left to go from these D-wave correlated bosons to now the D-wave correlated fermions, which is maybe more interesting because this is really where which directly connects to electronic systems also. And so the way how we produce D-wave correlated fermions in such a ladder is the same as for the bosons. We have a ladder with ring exchange interactions again. We assume that there are ring exchange interactions, and we also have strong on-site repulsion, which actually then in the case of fermions means that we actually don't really have a Hubbard lattice, but like a TJ model. So where we say we have like we limit the occupation of the fermions to one fermion per site, and only allow for virtual doubly occupied situations, which then leads to this super exchange Heisenberg type of interaction. And yeah, so that produces such a D-wave correlated non-Fermi metal phase, these ingredients. But what we then actually wanted to know is what happens in such a system if we add additionally this diagonal hopping term, which can actually, if you make it negatively valued, flatten the lower band of this of the tight binding model. So this is the without diagonal hopping, and then a slight or small diagonal, negative diagonal hopping flattens here this lower band. I mean, we can make it entirely flat if you want, but actually this is here the situation which we were interested in. And yeah, what you see then, so this work is done by João Mendonça, who was a summer student at DIPC last year, and in collaboration with a group of people around the world, or around Europe at least. What we found then, if you do the many-body calculation with this flattening term, this flattening hopping term, you see, so this is the situation without flattening, so the diagonal hopping 0. You have a Fermi liquid phase, and then at a critical ring exchange strength, you enter this non-Fermi liquid phase with a dxy pairing. And now if you flatten, then the system, by adding a negative value diagonal hopping, you see actually the Fermi liquid regime becomes smaller, and you do not enter the dxy phase directly. There is an intermediate phase, which is also a non-Fermi liquid phase, but now with dx square minus y square pairing. So this is already something interesting, that we get a different pairing symmetry, and we have the possibility to switch between pairing symmetries through this ring exchange interaction. But what is much more important, actually, in my opinion, is the fact that if you look here, this dx square minus y square paired phase, this extends to values of 0 ring exchange. So actually there is a chance of getting into this paired phase without any need of ring exchange interaction. And that makes it quite interesting, actually, then to talk to cold atom people, because cold atom people, they don't have ring exchange interactions, and they don't want to know about systems with ring exchange interactions. They can not easily engineer that, but they are very capable of producing this kind of lattices with additional hopping terms, and even making this hopping negative through, for instance, Floquet shaking. This is possible. So that actually is kind of like a feasible parameter regime here. And so that is actually our hope, that there can be a cold atom experiment and see this paired regime. Yeah, with that, I'm done. So I have shown you how we can use trapped ions to get this bosonic D-wave in a synthetic ladder, and I've shown you that in a fermionic ladder we can possibly get this for cold atoms through providing a diagonal, negatively valued diagonal hopping term. Thank you.
Well, thank you very much for actually being on before time, actually. So, questions, comments? I have to say that there's one funny thing. Actually, my first published paper was actually a ladder geometry using transfer matrix methods that Sunny mentioned to find non-trivial phases with qubit systems, when qubit was not a word. So many years ago. So with local interactions. So the thing is, what can be? So you were mentioning that this could be implemented in many different systems, but actually, why do you think the ring interactions are so crucial in the electronic case? That I didn't quite get. Why would you expect to have in any electronic system the ring-like interactions?
No, I mean, of course, people are more interested in electronic systems because most things are electronic in the world, right? And I mean, bosons are kind of exotic objects. So and with of course, with cold atoms we can study bosonic and fermionic systems, and that is, I think, yeah. That's maybe what I believe is in the moment a big issue in the cold atom community is to study Fermi-Hubbard model and find find pairing in Fermi-Hubbard systems, and this is so. I mean, in principle, it is believed that the Fermi-Hubbard system has if you dope it, you get a D-wave paired phase. but getting it, realizing it is complicated because it's at very low temperature, so so it's essentially a matter of cooling, and then I mean having something which can facilitate the occurrence of such a paired phase in a Fermi-Hubbard level, I think would be welcome, and I think as it looks like flattening the band through this diagonal hopping is a promising route, maybe to go there. So. But I mean, also, of course, I mean, if you had like a ring exchange interaction, then you can very straightforwardly go there, but that's not something which usually is available.
More questions? If not, let us thank Tobias and the other speakers.